There are buildings standing in Rome today that have survived more than 2,000 years of rain, earthquakes, seawater, and the slow weight of time. Not restored, not reinforced with modern materials, just standing. The Pantheon, the aqueducts of Segovia, the harbor walls of Caesarea, submerged beneath the Mediterranean for 20 centuries and still structurally intact. Meanwhile, a highway overpass built in 1987 requires emergency repairs. A parking garage develops dangerous cracks after 30 years. A coastal seawall begins to crumble before the engineers who designed it have retired. The gap between these two realities is not a coincidence. It is a question. How did builders working without computers, without modern chemistry, without precision instruments, produce structures that outlast anything we make today by a factor of 10, 20, sometimes 40 times over? For centuries, the answer was assumed to be simple. Roman concrete was just good craftsmanship. Dense, well mixed, built by an empire with unlimited labor and time. That explanation seemed reasonable. And for a long time, no one looked further. Some knowledge was never lost. It was simply waiting to be remembered. In 2023, a research team from MIT, Harvard, and universities across Europe published findings that changed how materials scientists understood Roman construction. They had been studying samples of ancient Roman concrete, the specific mix Romans called opus cementitium, using high-resolution imaging technology that did not exist a decade earlier. What they found inside the material had been visible for years. Small white fragments scattered through the concrete matrix, irregular chunks lighter than the surrounding stone. Previous researchers had assumed these were evidence of poor mixing, sloppy work, batches that were not properly blended before setting. They were wrong. Those fragments were not mistakes. They were the mechanism. Roman concrete was made using a process called hot mixing. Builders combined volcanic ash, seawater, and lime, not slaked lime carefully cooled and prepared, but quicklime, raw and reactive, mixed directly into the aggregate while still hot. The temperatures involved in this process were extreme. The reaction was violent by modern standards. And it produced something that modern Portland cement, the basis of nearly all construction today, does not produce. It produced a material with memory. When a crack forms in Roman concrete, something happens that does not happen in modern concrete. Water enters the fracture. That water contacts the unreacted lime clasts still present inside the material. The lime dissolves, and as it dissolves, it migrates toward the cracked surface, where it recrystallizes as calcium carbonate. The crack closes. Not metaphorically, not approximately. The material grows new mineral structure across the fracture and seals itself, sometimes within weeks of the damage occurring. Roman concrete heals. This is not a property that was engineered in any deliberate modern sense. Roman builders did not understand the chemistry of what they were doing. They did not have the vocabulary for calcium carbonate crystallization or reactive pozzolanic compounds. But they had something that took centuries of empirical practice to accumulate. The knowledge that this mix, prepared this way, using these specific volcanic materials from specific regions of Italy, produced structures that lasted. They knew it worked. They did not need to know why. The volcanic ash was essential. Romans called it pulvis Putiolanus, the dust of Puteoli, a coastal town near what is now Pozzuoli in southern Italy. This ash, formed from ancient eruptions, contains specific mineral compounds that react with lime and seawater in ways that ordinary sand and gravel do not. The reaction is slow, developing strength over years rather than days, and it produces a crystalline structure that becomes denser over time, not weaker. Modern concrete does the opposite. It reaches peak strength within a few weeks of pouring Then begins a slow process of degradation. Moisture, temperature changes, and the expansion of embedded steel reinforcement gradually fracture the material from within. Most modern concrete structures have a functional lifespan of 50 to 100 years under ideal conditions. Roman harbor walls, constantly battered by seawater, are measurably stronger today than they were when first constructed. Seawater, which destroys modern concrete, was apparently part of what made Roman maritime concrete more durable over time. This is the kind of finding that materials scientists find genuinely unsettling, not because it suggests ancient Romans were more intelligent, but because it reveals how much knowledge can be embedded in a practice without being formally understood, and how easily that knowledge can disappear when the practice is abandoned. The shift away from Roman concrete was not sudden. It happened gradually across several centuries as the Western Roman Empire contracted, and the complex supply chains that moved volcanic ash from Campania to construction sites across Europe and North Africa became impossible to maintain. The specific knowledge of how to source and prepare the correct materials fragmented. Different regions developed different local practices, and eventually, the particular combination that produced self-healing concrete was simply no longer being made. By the medieval period, the formula had been functionally lost. The rediscovery of concrete in the modern era came through a different path entirely. Portland cement, patented in England in 1824, is a standardized product. It is manufacturable anywhere using widely available limestone. It sets quickly, which matters enormously for industrial-scale construction. It is predictable in a way that made it ideal for the engineering standards of the 19th and 20th centuries. But it does not heal, and the incentive structures of modern construction do not particularly reward materials that last 2,000 years. Buildings are designed, permitted, financed, and constructed within frameworks that assume replacement and renovation as normal cycles. A concrete that requires repairs every 30 years generates ongoing economic activity. A concrete that stands unassisted for 20 centuries does not fit that model in any straightforward way. This is not conspiracy. It is structure. The conditions that produce a particular material also shape whether that material continues to be produced. What the 2023 research team demonstrated was not just that Roman concrete was better in certain applications. They demonstrated that the specific property responsible for its longevity, the reactive lime clasts that enable self-repair, could in principle be reproduced using modern materials and techniques. The hot mixing process is not mysterious. The pozzolanic ash can be sourced or synthesized. The chemistry is now understood well enough to be deliberately replicated. Several research groups and construction companies are now actively working on modern formulations based on these findings. Coastal infrastructure, underwater foundations, and structures in high-humidity environments are the most obvious initial applications, places where conventional concrete degrades fastest and where the self-healing property would have the most measurable impact. Whether this reaches mainstream construction practice depends on economic factors, regulatory frameworks, and supply chain realities that have nothing to do with materials science. Those questions remain genuinely open. What is no longer open is the question of whether Roman builders understood something about durable construction that was subsequently forgotten. They did. Somewhere inside walls that have been standing since before the concept of a nation existed on this continent, there is a process still occurring. Lime dissolving, crystals forming, cracks closing. The buildings are not just surviving. They are maintaining themselves with no input from anyone, using a mechanism embedded in them 2,000 years ago by people who had no word for crystallography. That is what was lost. Not a secret, not a formula locked away, but a practice so embedded in routine construction that no one thought to write down exactly why it worked. And when the conditions that sustained the practice collapsed, the knowledge collapsed with them. The Pantheon is still standing. The concrete inside it is still doing what it has always done. Some knowledge was never lost. It was simply waiting to be remembered.